Well, it's Saturday, so I have been doing videos on quantum theory, Schrodinger's course. Will it be a course? Will it not be a course? This was Schrodinger's video for a while there. I wasn't sure if I would do a video today or not. It may be relatively short. Um, Today's video is on the photoelectric effect. So Planck really didn't like his hypothesis. He was hoping there was something about the atom maybe that caused it to come out in packages, and or that the formula worked because of certain peculiarities of the atom and so forth. He didn't want to believe that light really, or that energy really existed in discrete packets rather than a continuous spectrum of energy and such. He didn't want to think that. But Einstein was a young'un. He was 25 in the year 1905. He was working as a clerk at a patent office, I believe, and but he's obviously a bright fellow. And Einstein, because he was, I think, this is one of the things when you're young, you tend to be more open to new ideas. When you get older, you tend to kind of want to go with the ones that you've had for a while. And in fact, maybe if you're a scientist or a scholar, you've maybe written some things even. So to change your mind would mean you'd have to admit that you were wrong about something you'd done. Anyway, this is a little personal commentary here, but these were personalities, right? They're not just brains in a vat. They're people. They're emotional. They have biases. Einstein certainly had biases, as we've seen and will see with regard to quantum physics. But at the young age of 25, he was open to new ideas. And he actually published 3 articles in 1905 at the age of 25. He published one on the special theory of relativity. That's the one that we now would say was the most significant of his articles in terms of history. However, at the time, his article on the photoelectric effect would win him the Nobel Prize for Physics. He didn't actually win the Nobel Prize for Physics on relativity because it took a little while for that one to really become widely accepted. In fact, I think it was 1919 when a particular experiment was thought to support it. I think it was done wrongly in retrospect, but it's one of those where you come to the right conclusion, but for the wrong reason. But anyway, Einstein's article in 1905 on the photoelectric effect actually won him the Nobel Prize. And in that article, what he did is he took Planck's assumption and applied it to a phenomenon that had not been up to that point explicable. So the phenomenon is basically that if you shine a light or ultraviolet radiation on a metal plate, you'll find that photons jump off the plate. It's kind of like, oh, it's hot in here. Have you ever stepped on a hot surface and kind of, I want to get off of this. When you put incident light and radiation on a metal plate, you will find the photons jump off. And get out of there. What was curious is, however, that as you increased the intensity of the light, if you kept the frequency the same. Now, if the frequency of the light was the same, but you increased the intensity of the energy, or not the intensity of the light, there were more photons jumped, but they didn't jump off with more energy. That is, that the energy with which the photons jumped off the surface remained the same. If the frequency on the metal plate remained the same, the energy of the photon, if the frequency at which the energy coming on the plate remained the same, then even though if you increase the intensity, the number of photons jumping off would increase, the energy level that they jumped off with would not remain the same as well. Let me try that one more time. That if you shine radiation on a plate, photons jump off. If you keep the frequency the same, the energy of the photons are going to remain the same. More intensity, you're going to get a larger number of photons jumping off, but still at the same energy. Now, what the experimentation also showed is that if you increase the frequency, if you turn up the frequency of the incident radiation, there is a threshold frequency at which the energy jumps. Now, the energy doesn't change up to that point, but at a certain threshold frequency, and it differs for different kinds of metals, but at a certain threshold of frequency, then the energy jumped. And actually, it increased from that point on. And basically, Einstein showed that this verified that what Planck had discovered was not just some quirk of the atom, but in fact, that it was part of the nature of energy itself, that energy exists in packets. E equals h nu. Remember that? E equals Planck's constant times the frequency. And so you can see that if the frequency stays the same, E equals h nu. If the frequency remains the same, the energy remains the same. But if the frequency gets beyond the threshold, then as frequency goes up, the energy will go up as well. And the threshold is, I think, related to Planck's constant. So this was the knockdown, drag-out proof that, in fact, Planck had discovered something about reality and not just something about a quirk, or a trick. Well, I hope to write that up at some point, but I still don't have it firmly enough, or I don't have it deeply enough in my understanding to know exactly how to write that up. But it is part of the story, and so it's appropriate in this. Is it Schrodinger's course or is it not Schrodinger's course? It's certainly Quantum Saturdays as we go on this quantum journey, trying to learn a little bit about quantum physics, possibly using ChatGPT along the way, although I didn't use it today. Coming to you today from Canada, from Ontario. I should, Lord willing, be back in Indiana next Saturday.